In this video, we will discuss how to differentiate power series term by term, and we will do that with the use of the following theorem. The theorem states that if we have a power series such as this one centered at some value c, and the series has the radius of convergence r, which is some positive number, then the following is true. The function to which the power series converges on this interval, let's call it f of x, is then differentiable and therefore continuous. On the same interval and moreover, the derivative of this function can be found and expressed as a power series, and it's going to look like a formula, but we actually don't have to memorize this formula because this is nothing but what we call a term-by-term differentiation. So this series is obtained from the one on top by simply differentiating each term of the series with respect to x. And always this derivative can be rewritten, or rather reindexed, so in the following way. And this process is called term-by-term differentiation. Now, I should mention that the interval of convergence of the new of the derivative function is at least as big as this interval. The convergence may change at the endpoints, so we're not really sure if c minus r or c plus r are the parts of the interval of convergence of the new series. But to avoid like this constant check, we're just going to keep track on the radius of convergence r. So instead of writing out the interval of convergence, which implies that we know whether the endpoints are included or not, we'll just avoid that by always mentioning the interval of the radius of convergence r instead. So that doesn't change. And to understand this, what we just did, let's do an example. So let's start with the well-known identity, and so the radius of convergence here is 1, meaning that the interval of convergence, of course, in this case we do know, but as we find the derivative, we will lose that knowledge, but we will know that the radius is still 1. So the question here is, what happens if we take this identity and differentiate both sides of it with respect to x. And on the left hand side, we just have a derivative of a function of one variable. So we're going to use the chain rule. It's going to be -1/1 minus x squared times derivative of 1 minus x, which is just -1. Now, what do we have on the right side? And this is exactly what the theorem addressed. It tells us exactly what's going to happen on the right side. On the right side, we're going to have the following power series. And this is what we call the term-by-term differentiation. So to differentiate the whole series, we're just going to differentiate each individual term. And what's the derivative of x to the n? It's just n times x to the power n minus 1. However, I made this mistake on purpose, or maybe not, but I want to draw your attention to back to the statement of the theorem and show you that if the original series starts at 0 and ends when n equals 0, we have a constant term. When you differentiate, the 0th term kind of disappears, and therefore we bump this index up by 1. If you keep it 0, well, then n is going to be 0, so it's still going to disappear. So it just makes sense to bump it up by 1, so that when we change the index, when we reindex our series here, everything still makes sense. So going back to our problem, and with that index in mind, with the change of index in mind, we're going to come back here and we're going to start at 1. And now the only thing that's left for us to do is to simplify both sides here. So the left hand side became this function, and the right hand side we can leave it as this, or we can reindex it and start it at 0 by adding 1 to every n inside of the sigma, and then the answer, what is the power series of this function, then is the following. Right, so this is the general formula, and of course we can write a few terms. When n is 0, we have 1, then we have x 2x, 3x squared, 4x cubed, 5x to the 4, etc. And if we ask what is the interval of convergence, the answer is, well, we know that this is the smallest it would be. However, we're not sure whether to include these points or not. So instead of checking the boundaries, we're just going to say that the center of convergence is 0 and the radius of convergence is 1. And that's more or less describes the interval of convergence without getting into those details about what's going on at the boundaries. And well, this is an example of a term-by-term differentiation. Let's do another example. Let's try to answer the following question. Find the first 5 terms of power series representation of this function. And this is not a function that we have seen before, so the question is definitely not trivial. However, we're gonna start by observing the relation between 1 over 1 minus x squared and this function. And in particular, I want to notice that if we take 1/2 of this function, so if we take 1/2 of this function and then take the derivative of it, then we're going to get, per chain rule, we're going to get negative, so we're still going to have 1/2, then we're going to have negative 2 over 1 minus x to the power 3 times the derivative of the denominator, which is negative 1. And as you can see, after everything is reduced, we end up with exactly the original function. So if we want to find the power series of this function, which is what the task is, we can start by taking the derivative. So I don't know what that series is yet, but we're going to differentiate the series. There is a power series representation of that 1 over 1 minus x squared, which we just found earlier. So the series that we're going to differentiate is this. And according to the theorem, we can differentiate this term by term, and whatever that answer is, that's our desired answer. So let's do the derivative. It's going to be, let me bring 1/2 inside. The index is going to go up by 1 per rule. Now we're going to have the derivative. N plus 1 is a constant, and we're going to bring another n down and take 1 away from the power. So this is the answer. And now we can, I guess, conclude. Let me make a little bit more room here. We can now conclude that the function power series representation of which we were looking for is equal to, and we can change the index. We can reindex it to start from 0, and then it's going to be 1/2 n plus 2 n plus 1 x to the power n. And all of this is true around c equals 0, and the radius of convergence is 1. And again, this is our way of avoiding getting into that conversation about whether it converges or not at the boundaries of this interval, that is at -1 and 1. So this is again our function. This is the power series associated with that function, and this is a statement about the interval of convergence. Now, another good exercise here could be doing the following. If we assume, we don't know that yet, but if we assume that the following series converges to cosine of x everywhere, right? So the radius of convergence is infinity here, and the question would be find the power series representation for the sine function. And what we know about the sine and cosine is that one is the derivative of another one. So if we're looking for a power series of sine, then what we can do is we can take the negative cosine of x function and take its derivative. And this is one way of getting sine of x. And if we take negative cosine, then according to our statement above, the power series for negative cosine will be this. Now we can bring this negative 1 inside of this series just by adding another negative 1 over here. And now to obtain the power series of sine, we're just going to differentiate this term by term. And when we do so, n will become 1, or rather the starting point, the starting value will become 1. And now we're going to differentiate this. So we're going to have nothing changes here. We're gonna have to bring 2n out, or rather down from the power, and then subtract 1 over here. And we're going to divide by 2n factorial. So this is what the derivative of this series is. And now I'm just going to continue writing it out carefully. First, I'm going to simplify what's inside of the sigma. The 2n will be reduced with this 2n factorial in the denominator. And then the only thing that's left for us to do is to reindex it. And we reindex it by changing the starting value back to 0, but adding 1 to every appearance of n in the expression. And here's what's going to happen. So here we're going to have negative 1 n plus 2, but it's exactly the same as negative 1 to the power n, so I'll just remove the plus 2. Here we're going to have x to the power 2n plus 1 minus 1, but that's exactly, after simplifying it, that will just become 2n plus 1. And here in the denominator, we're also going to do the same thing. We're going to have 2n plus 1 minus 1, but simplifying it will just give us 2n plus 1, and we still have factorial. So what we learned here is that if what above is true, then the power series representation of sine of x function is this. Right over here. And the radius of convergence is still infinity, right? So that didn't change. So what we learned in this lesson is how to differentiate power series term by term, and by doing so we can obtain new relations and find new power series, or find rather power series representations for new functions.